Swayam Prabha. Digital India. Educated India.
Welcome back. So let's continue the discussion of Flamelet equation for non-premixed combustion, and we have looked at the adiabatic system and non-adiabatic system. Now we are looking at how we can model this Flamelet equation. So we had looked this non-adiabatic system and adiabatic system, and now we look at when you have under this turbulent condition mixture fraction and stoichiometric scalar dissipation rate, they are fluctuating. So you need to define this PDF or probability density function of Z and stoichiometry. So once you define that, this has to be found, that means the joint probability density function, this is again the Fabry averaged terminology. So then you can find out your mean species mass fraction using 0 to 1 and 0 to infinity. This is mass fraction variable, which is a local flame structure. This is our local flame structure, and the probability density function. Similarly, mean temperature one can find out using the local variable of the T and the PDF function. So this includes the effect of turbulent movement, flame position, finite rate of kinetics, everything. So that's how you obtain from there. Now if we assume, this is again a specific case where we assume that Z and stoichiometry are statistically independent. If it is statistically independent, what we have already seen in statistical description of the turbulence, this joint PDF function, which is a function of Z, and we can write in individual function like this, Fz and F stoichiometry. In that case, what will happen, that this calculation of the mean mass fraction or calculation of the mean temperature can be modified. This is again local flame structure, and this is you get your this, that is the density function for mixture fraction. This is the PDF function for the stoichiometric scalar dissipation rate. So PDF mixture fraction assumed to be a beta function, and PDF of scalar dissipation rate assumed to be a delta function, no fluctuation, it is a log normal distribution. And sometimes that is why literature you can see this presumed PDF approach is also called the beta PDF approach. This is another terminology which you may come across while looking at this thing, because that is how you assume the shape of the PDF to find out the mean profile. Now for the scalar dissipation rate, if you look at the normal profile or normal distribution, log normal distribution, this is how the probability density function PDF of the stoichiometric scalar dissipation rate, which is written, this is 1 by stoichiometric sigma exponential to the power this. Now here the mean of scalar dissipation rate would be exponential mu plus sigma square by 2, and the variance would be exponential like that. Now if you look at the plot, this direction is the scalar PDF of the stoichiometric scalar dissipation rate, and this direction we are plotting the stoichiometric versus the mean. It is a sort of a ratio, and for different variance sigma 1, sigma 25, you will see how this log normal distribution varies. So this is an already assumed function, that means the a priori I know the probability distribution function, which is an advantageous compared to solving the individual PDF transport equation, which is quite expensive in nature. So, that is another aspect of it. Now, if you look at the spatial profile of the scalar dissipation rate in counterflow laminar flame, this is how along the Z and this is the reduced coordinate, this is how it moves. This already we have seen, there is nothing like that. Now, the point which is quite important is that how we estimate the mean scalar dissipation rate at the flame position. So, we estimate the unconditional mean of scalar dissipation rate, which is like this, which can be estimated like C phi density epsilon by k and mixture fraction variance. Now, C phi is a model constant and typically value of 2 is used. Now, this is essentially a constant which takes into account the ratio of the time scale between flow and kinetics, and here is the time scale of the turbulent structure epsilon by k. So, that is why large or wide range of problem this model constant of C phi equals to 2 works nicely, but when you go to some specific cases like hot flow conditions and all these, where auto ignition is is the primary dominant mechanism, that time, or rather where the flame is kinetically controlled rather than the mixing control, this value may not work, one has to tune it. Now, if you look at the scalar dissipation rate profile at constant density, this is how one can represent this, and this will get you the mean scalar dissipation rate in terms of 0 to 1 like this, and you can do the simplification and get like that. So, essentially if I put these things together, that is how you have it from your completely strange laminar flamelet model and how it works. So, you solve the mean flow field along with turbulence, this is your turbulence equation, this is our mean field, okay, and there, since this is an flamelet approach, one information which is required is the local flame structure. This is our local flame structure. So, all your species, mass fraction, temperature, these are solved using detailed kinetics and the values are stored. Now, first thing what happens is that using the information of mixture fraction and its variance and also the information of the turbulence, we first feed in there and we get the probability distribution function of the Z. This is the probability distribution function, and that we have seen how we can obtain that. That is essentially a gamma function, and using the Z and Z variance we can do that. Now, we have an also presumed probability distribution function from the xi, which is a log normal distribution. Now, we feed the information of the Z and Z variance here and model xi as a function of k epsilon and variance square, which is xi is C phi epsilon by k into mixture fraction variance. Now, we can model for mean stoichiometric scalar dissipation rate, which is a function of Z and the shape function. So, using this distribution function and also the information of mean scalar dissipation rate, we find out this. So, which will give me this presumed PDF of the xi t, which typically is the log normal distribution. So, that means when you looked at the equilibrium set of calculations, this portion was not there. We had a distribution function of Z, local flame structure from the equilibrium, and they used to get it. Now, here you get Z and Z variance, using that you calculate psi, the scalar dissipation rate, psi chi to stoichiometric scalar dissipation rate, mean and and then finally the distribution function. So this one and this one together with the local flame structure get me mean temperature profile or yi, all this, and then finally you get rho and viscosity. If it is temperature dependent, these will be fed to the mean profile. That means again these are the properties like density, transport properties, they are sent back to the mean flow field, and mean flow field is actually taking those things into account and it solves for the mean flow field. So this is how the mixture fraction based situation actually works. Now if you look at some of these examples, so this is taken from this literature. This is a natural gas flame. Here is the mean temperature profile and laminar flamelet model, where you can see the predictions how it is obtained. This is the flame structure and so. So now this is another for the same using this flamelet model, how we get the radial distribution of the temperature, these things. So there are some over predictions of the local extension, because this temperature profile is over predicted as the flamelet model does not take into account the local extension. Okay. So this is what give you an idea. If you look at this literature, this will give you an idea the different issues of flamelet model and all these things. So that's pretty much what you have in the flamelet zone, and if we put them what we have discussed. So one is that flamelet models are based on completely flame normal analysis, which is absolutely important, because that's where if you have a local flame structure like this, and this is how in the along the normal direction we do the calculation. Now flamelet equations which are provide the profiles as a function of mixture fraction for a cross section normal to the flame, but they rely on the diffusivity, equal diffusivity assumption. This is an important assumption. Now third, the laminar counterflow diffusion flame equation, which can provide the function of distance, profiles which are converted as a profile of mixture fraction. Now the important is the turbulent flames in the limit of high Damköhler number can be described as a statistical ensemble of laminar flamelets. The probability density function of mixture fraction is determined from calculated mean and variance and assumed shape. So this is what it is done in to estimate the realistic situation. So that's pretty much what or how you get to the laminar flamelet kind of system for the non-premixed case. Now we can look at some comparison of this flamelet model and the PDF model, and that will give you what we have discussed so far for this under this non-premixed combustion. Everything will be qualitative and it will give you quick refresh of the whole thing that we have talked. So first look at the strained laminar flamelet model. This is again another name is that presumed PDF or beta PDF approach. Okay. So we have a Rand's equation where mean field are solved. Then we have turbulence equation where the turbulence informations are coming into the picture. In the mean flow field equation we solve mixture fraction and its variance. So using that we get, and using the turbulence information also we get scalar dissipation rate, which is estimated like that, mean scalar dissipation. From the mean scalar dissipation rate we get stoichiometric scalar dissipation rate, which will lead to this presumed shape of the probability distribution function of the that. And then same thing, using the mixture fraction and variance we get the presumed shape of the PDF for the Z, and these two PDF along with the local flame structure which is a priori calculated, we get all the mean profile. And then finally all these transport property which are sent back to the mean flow field equation to make the handshaking. So that is what we do. One thing, it is very fast, computationally less demanding, and can be applied to a large scale of problems. Now this is scalar PDF equation, that means, or it is an transported PDF approach. There under that it is a compositions PDF, composition or scalar PDF. Here we solve the transport equation for the probability density function or probability distribution function, and this is where it is a computationally expensive procedure. We adopt hybrid method. So that hybrid method is we solve both Eulerian and Lagrangian. So this is where we solve the mean flow field, we solve turbulence also. So these are turbulent, mean flow field calculation. So the turbulence equation, using that we get the turbulent frequency. Turbulent frequency goes to estimate the micromixing model. At the same time, mean flow field information passed, turbulent frequency is passed, micromixing model, using that we solve the Lagrangian equations in the Monte Carlo system, where these are input, turbulent frequency input, mean flow field information, mixing model, reaction model, everything is there. So there we solve individual particles, or this is solved in the particle approach. So particle position, their reaction, mixing, and all these things are taken into account. From here we estimate again density and other transport properties like viscosity and all these things which are sent back to the mean flow field equation. That means if you look at it, the commonality between these approaches, whether transport PDF approach or the presumed PDF approach, the mean density or other transport properties are which are coming out to be the parameters, they do the making that bridging between the mean flow field and the local situation. This is again transported PDF approach. But this is now velocity scalar composition PDF. That means you require joint PDF and all these things. So idea is similar. You solve here mean flow field. Here you solve specially RSM kind of equations, where you have individual Reynolds stress term which are solved, and also the dissipation which are solved, and using that you get turbulent frequency, and that is passed for the micromixing model, and that information is fed, frequency is fed, mean flow field information, kinetics comes here, then the Lagrangian solutions are obtained in Monte Carlo technique, and using that finally again the density, viscosity, these are the parameters or which will be fed to the mean flow field equation, and we solve for that. Now if we look at these flamelet models and that issues, the problem here, equation for the mean quantities are unclosed. So that is why the problem is split into two problems. One is the mixing problem, which is the mixer fraction, and a lookup table which is calculated or pre-calculated using the local flame structure known as flamelet depending on a parameter of scalar dissipation rate chi. Now, this is one of the problem which are handled in this way, and that is why make this process to be generic enough. Now, the second problem which is there is the turbulence can lead to presence of more general flame structure different from the pre-computed flamelet structure. There are one way to solve this problem: extend the library for pre-computed structure with triple flames or with igniting and extinguishing flamelets. So, that will allow to at least go to certain limits, or alternatively one can introduce another scalar transport equation in terms of flamelet, a progress variable, and take the source terms of progress variable from flamelet, and this is going to be FGM kind of approach, that is the flamelet generated manifold kind of approach. So, that means not only depending on the local value of mixture fraction and variance, also you solve for the flamelet progress variable, and now using those information you can actually sort of handle this kind of problem. Now, a model for joint PDF or independent variable is needed. This is another issue that one has. Now, these are the some of the problems one can think about while looking at. Similarly, if you go to the transported PDF approach or Monte Carlo based PDF method, so one problem, equation of the mean quantities are unclosed obviously, but the chemical source term remains closed. So, using the description of probability density function, the source terms are, the other terms are closed. Also, another problem which comes in is this problem, that the exact equation for the PDF is also unclosed. So, we use some approximation for that and using the mixing model to close that term, and the scalar dissipation rate, which is the chi, that appears in the mixing model. But now the mixing model or the accuracy of the mixing model or the fidelity of the mixing model can have lot of impact on this thing in closing these terms. So, that is another point here, because one has to look at what kind of mixing model or what, because we have already seen 3 different kind of mixing models. Now, third problem is that solving PDF equation by finite volume kind of methods are quite expensive, which is true, and that is why we go back to particle kind of situation or Monte Carlo kind of situation. So, that is one of the most efficient method to solve it. Then obviously you do some trade off in the solution using some sort of a simplified chemistry, that means you do the reduction instead of using detailed chemistry, because more and more chemistry if you used, it would be computationally really expensive. So, that is another. Then use some fast tabulation and retrieval algorithm, that means the tabulations and the retrieval, if it is, this is something to do with the programming skill, because one has to write the IO functions to be efficient and optimized. Then you can use a flamelet generated manifold, same as in the case of flamelet model, but the PDF is not assumed or calculated. So, now if you see this, there are this is all discussion on something which is related to the PDF kind of model, that is one way you can have presumed PDF method or beta PDF method, where it is computationally less demanding, it is quite fast, can be used for wide range of non-premixed combustion models. But when you look at the Monte Carlo based method, they are expensive. Obviously, you do not have to assume the PDF distribution a priori, so it could be accurate, and this provide reasonable a good prediction for the non-premixed cases, and premixed cases you require fine tuning, but theoretically this should be applied to any mode of combustion. So, that is what it is. So, that is pretty much, if you look at this chart, we have pretty much covered all this discussion except this last one which we are going to now do. This is one of the advanced model. So, you have to refer to the literature, and there is another advanced model which is called MMC models. So, this CMC is conditional mapping closure and this is multiple mapping closure, and we will give you an idea, or we will do some discussion on CMC, and MMC will do while talking about the multi-phase flows little bit. So, that will give you how we started with the simple reaction models, then issues that we have discussed, then move to the statistical based model, then finally some models for premixed combustion, then we have looked at non-premixed, and now we are going to look at this CMC one. Now, here the instantaneous balance equations, we have to start from that our basic set of equations which are continuity, Navier-Stokes, species mass fraction, source term which we will get back, and the enthalpy equation, I mean the total enthalpy which is chemical and thermal. So, you get heat flux, heat source and other term. So, if you put this scalar variable, this would be the function of, I mean it is a set of scalar variable which will include all the mass fraction and enthalpy this. Now, again we need the definition of mixture fraction. So, the fraction of the mass which is present locally, and we will get the mixture fraction transport equation. I mean this is again free from source term, the I mean chemical source term, that is a biggest advantage of that thing. And then you put the boundary condition, this is in the oxidizer inlet and this is fuel inlet. So, Z 0 and 1, so Z will vary between 0 to 1, and the reactions takes place along Z stoichiometric, right. And if you have fast chemistry model, then you get, this is the continuity, momentum and the mixture fraction equation. So, here Yk will become a function of mixture fraction and scalar dissipation rate, and the fluctuation in mass fraction determined by the fluctuation in Z. So, that means this is Yk prime and this is Yk. So, one hand, so this would be function of Z variance, and obviously Z has to be there. So, you can take into account the function like this in the fast chemistry models, and these are detailed discussion that we have done that. Now, we can see the different relationship, but that we will do in the next class. We will stop here today. Thank you.